All right, so in Gen Chem, we learned about resonance structures and we drew resonance structures, and we're going to continue to do that in organic chemistry, but we're going to take it a step further, right? So in organic chemistry, we don't just show resonance structures, we also show how they're related. So how do you go from one resonance structure to another resonance structure? And the way we do this is through what's called kind of arrow pushing. And so what we have is an arrow with an arrowhead on it, right? And so this is the tail end of the arrow, and this is the head of the arrow. And some things that you need to know is that the tails always start at electrons, right? What we're showing here is the flow of electrons, right? So this tail end of the arrow has to start off at some electrons. The head can end up on electrons, bonds, atoms, a bunch of different things we'll see. One other thing that you need to keep in mind is that this needs to be kind of a double hook arrow. You cannot draw this kind of half hook arrow. That represents something else, and we'll get into that later on, right? So you can't do that. And another thing that we need to realize is that we're going to use this arrow pushing mechanism later on. And although it looks the same in terms of resonance structures that we're learning about now and mechanisms that we're learning about later, they're actually a little bit different. So this is a bit confusing. What we need to keep in mind is that resonance structures don't actually resonate between each other. Right, so it's a bit of a kind of a dumb name, but it is what it is, right? They don't resonate from the structures, right? It's not like this structure is going from one resonance structure to another. It's that the real structure is a combination of all the resonance structures. And so for now, our arrows are just theoretical. So they don't show the flow of electrons. They just show how these two structures or multiple structures are related to one another. Later on, they will show the flow of electrons when we get to mechanisms. So let's go back to our allyl cation, right? We draw two resonance structures for this, right? The one on the left and the one on the right. And now we need to show how we get from one to the other. And so remember, all we're going to do is move some pi electrons. So the electrons in this bond moved to the other side. And so we can show that using arrows. And so what we show is that these two electrons in this pi bond move over to this other side. And then we get the structure on the right. And then to go from the right to the left, the double bond simply moves over to where it was. And then we get both compounds, right? So you can see how the arrows show how you get from one structure to another. So let's learn some do's and don'ts of drawing these reaction mechanisms or these resonance structure arrows. The first rule, and one of the most important rule, is don't break single bonds. Remember, with these resonance structures, all we're moving is pi electrons, and so we can't move any of our single bonds because those are made out of sigma bonds or sigma electrons. So for example, let's say you had this cation. Maybe you might be tempted to move the electrons over here, and then your product would end up looking something like this, right? So we broke a single bond here. You cannot do that. And so this is just a big old no. And you can tell it doesn't make a whole lot of sense because these two are completely different molecules. And in fact, the molecule on the left is one molecule, and then there's two molecules on the right, right? So we can't break any single bonds. All we're going to show is the flow of pi electrons and lone electrons, right? So that's kind of our next little step. Resonance structures only show movement of pi and lone electrons, right? Pi and lone electrons only. So for example, in our acetate, ion, we could draw these lone electrons moving into this bond, and then one of these pi electrons moving into the oxygen to get our other resonance structure. And then we could draw the reverse as well to get back to our original, right? So you can see how these arrows show how we go from one resonance structure to the other resonance structure. So we can't break single bonds. There's another thing that we can't do, and that's second row elements, which is mostly what we're going to be focused on. Carbon, nitrogen, oxygen, fluorine can't. They cannot break the octet rule. Specifically, they can't have more than 8 valence electrons, right? They cannot have more than 8 valence electrons. And so let's go back to our previous acetate ion example. And let's see what happens if we just try to do this step first, right? If we just try to do this step first, what's this resonance structure going to look like? Right, that's what it would look like right there. And then remember, there's a carbon right here, right? There's a carbon in the center right here. And now it has 1, 2, 3, 4, 5 bonds or 10 valence electrons, right? You can't do that. This is not a valid Lewis or a valid resonance structure, right? So in this example, you have to do both of these arrows at once to ensure that carbon does not have more than 8 valence electrons. Another example, something like this, right? And something that you have to kind of keep track of is to remember that your lone pairs don't have to be explicitly shown, right? So, right, this is totally fine. We don't have to show all the lone pairs. So maybe you're thinking you can move these over here. But we can't do that. Why can't we do that? Remember that this central oxygen has 2 lone pairs in this structure. And so it'd have 2 lone pairs here. And then now it's got 10 valence electrons. And so we're not allowed to do that. So no. So it is a little bit tricky because you really have to be good with your skeletal structure drawings and know when you have lone pairs and know when you don't have lone pairs, even though they might not be explicitly shown. And so while we can't have more than 8 valence electrons, we can have less. Having less is okay. So we can have less than an octet. So for example, if we had this compound right here, we could move the electrons in this pi bond onto this oxygen to draw a resonance structure and end up with something like this, right? This oxygen still has 8 valence electrons, but now this carbon here only has 6 valence electrons, right? There's no hydrogens attached. That's okay. The resonance structure on the left is still better than the one on the right because of the lower formal charges, but it's okay to have less than 8 valence electrons, right? And this structure overall makes sense if we think about our compound here. Oxygen is more electronegative, so this is partially negative, and this carbon is partially positive, which is kind of what this resonance structure is showing. And so at this point, I'd recommend that you really stop and do some work along problems, right? We're gonna get into a little bit more complicated scenarios, so you wanna have a good basis of the basics, and this is going to be a fundamental skill that we're gonna use during the entire course. So it's really imperative that you understand resonance structures very, very well.